Howdy and welcome back. So binary search tree class setup and node configuration. We'll go ahead and start with the node because that's going to comprise our elements of the binary search tree that we're going to implement. So notice in the previous lessons, I essentially introduced a type called binary search tree node. I don't want to type all of that today, so we're just going to call this thing node. What's in a name? I mean, as long as it's descriptive, I think that's the important in here. I think this is going to effectively communicate that the type of object we're dealing with is a node, and the application is going to be our binary search tree. Anyways, let's go ahead and decompose this. If you remember what makes a binary tree, well, it's going to be the fact that its nodes will be comprised of at most 2 children. We introduced this through these silly little diagrams, but remember that it's going to have, each node in our binary tree is going to have a pointer to the parent. There is going to be a pointer provided the object exists, a pointer to the node to its left, and then provided it exists, a pointer to the node on its right. We said for our, and again, there's these pointers back to the parent. Okay, there's my artwork for the day. I hope you all can appreciate that. But okay, so we have this thing set up, and what I mentioned was we're going to have a parent, we'll have a left, right, all are going to be pointers to other nodes corresponding to that of their name. We're then going to have some element of type T1, the data, which each node is going to house, as well as an object of type T2, which will be the key for a record within our binary search tree. Remember that how we kind of introduced this was, well, you might want to store student objects within your binary search tree, right? Or binary tree, binary search tree, whatever sort of tree structure we're building. Let's go ahead and assume we're storing some kind of complicated object. So a student might have a vector of courses. They definitely have a first name, last name. And then how are we going to uniquely or identify those records without actually having to go ahead and look into that object? Well, we could store a key value, which might be, for the student example, a student's UIN. Anyhow, let's go ahead and just, set this up now. So we're defining a class template here, node, and there's going to be 2 type parameters, T1, T2. When we instantiate this for maybe say a node of strings and integer objects, T1 is going to be initialized with its argument, type string, T2, in this case, int, which would effectively make data of type string, key of type int. And then we have these pointers laid out as we've effectively communicated within our UML diagram on the left. And notice that I'm initializing them. I'm providing an in-class initializer such that each will start out as the null pointer. Okay, let's get into what we're going to be doing today. We're going to be implementing a binary search tree. This will be a class template, and it will have 2 type parameters, T1 and T2, which are effectively used within the initialization of the node objects that are comprising our binary search tree. So if we go ahead and look at this definition here, I'm restricting this to the things we're going to talk about today. We see a default constructor. We see a parameterized constructor, which will take some data as long as some key value. In addition to that, we're going to see that because we're going to be dealing with the dynamic structure here, we're going to see that we're going to need to implement the destructor. So just to be complete, I'm showing here that, okay, in practice, we'd have to define a copy constructor, but I'm going to go ahead and delete that here so that we don't have to implement it together. That might be a good test question. So I might focus on, running through and implementing that on your own. Same with the copy assignment operator. I'm going ahead and providing its declaration here to remind you of the rule of 3, because we will be defining a destructor. So if we're defining one of these 3 functions, we probably should go ahead and define the other 2. Okay, so we'll get into the construction. So building this thing up, as well as the teardown process. And in between, we'll talk about inserting nodes into our tree. Our insert function is going to take 2 arguments, one of type T1 for data, another of type T2 for the key value. And we'll go ahead and use the data and key in both our parameterized constructor as well as our insert operation to create a node of type T1, T2. Finally, this clear function here, I'm going ahead and, so for the destruction process, I'm going to introduce this using a traversal on the tree, where we're going to visit each node and invoke the delete operator on each of those nodes in a sensible way, sensible order, we could say. I'm going to call my clear function within the destructor, and I'm going to have clear perform all the heavy work. Okay, this is going to be a recursive function call, and I'll get into this in a bit. But what we're going to see here is that I have overloaded clear to also have a definition where it takes a single pointer to a node object. And we'll see how we can leverage this in our recursive definition of clear, and effectively what the clear function with an empty parameter list is going to do is simply call our recursive clear, passing it the root, the pointer to the root of the tree. I'll try and decompose this a bit better. I know there's some ham wavy going on here, but I'll set it up when we get to it, and we'll see how, okay, the destructor is going to call this clear function, which in turn is going to pass the root to that parameterized version of clear. But that's our setup today. I hope you see where we're going with this. I guess I should have noted that, hey, in addition to the behaviors that we've just described, our binary search tree is going to have a single private data member. It's going to be named root, and it's going to store the address, so it will be a pointer to a node of type T1, T2, where T1 and T2 will be whatever types were used to construct our binary search tree. Okay, so let's go ahead and get into the destruction of our binary search tree objects here.